Hello calculus students. I am unfortunately at an all-day meeting in central office, so I can't teach you logistic growth. Hopefully you have picked up a warm-up with this problem on it. Notice it is from 1989 and it is an AB problem, and to be honest, it is not common anymore to have these kinds of differential equation problems on free response. They tend to be incorporated maybe in another kind of free response, but they're not just about the exponential growth problems. So, but it is good practice for A, our test, and B, similar problems to this will probably be found on multiple choice. So the first thing I want to highlight, and what happens in May, is that you forget this is a separable differential equation. Remember, always, I don't care what letters they have, V's, W's, U's, T's, whenever you have a derivative and you've got the derivative of y, or whatever letter this is, and you have that same letter on the right side, that is separable. If you also remember that this separable differential equation represents exponential growth and decay because it is the ky problem, or the proportion, and again, what if it wasn't, what if it wasn't a y? What if it was dp dt is equal to kp, or dz dt is equal to kz, or God forbid, what if they made that constant proportion? What if they made the constant proportionality little p? What if it was ds dt is equal to little p for proportional to s? Anytime you see a differential equation where the variable on the left side that you're taking the derivative of, right, which is the dependent variable, is over on the right side of an equation, that is separable, and you have to separate before you differentiate. But AP does allow you, especially if it's multiple choice where no work is shown anyway, that you don't actually have to solve this differential equation, right? We learned this yesterday. You can actually recognize, since that is a separable differential equation of exponential growth and decay, you can already here go directly to, notice they don't say solve the differential equation. They ask just you to write an equation for y by itself. And if you remember that y is equal to the initial y e to that constant proportionality times t. And now you just have to solve. And what information did they give me? Initially there was, so at time 0, I have 10 to the 6th gallons of oil, units. And 6 years later, there were 500,000. So those are my two data points. I can immediately replace y sub 0 with 10 to the 6th, and now I can use my other point to solve for k. So dividing both sides by 10 to the 6th. E to the 6th times k, right? 10 to the 5th over 10 to the 6th simplifies to just 5 over 10 to the 1st, and of course that's just 1/2. How do you get a variable down out of exponential land? Naturally. again, using my calculator, I get this to be approximately negative 0.115, but since I'm going to be using this value inside calculations, the directions on AP expect you to not round until the end, and I have a calculator with this, I'm storing this in alpha, and just to be cute, K. So my equation, my answer to part A is y is equal to 10 to the 6th e to the kt, but I have defined k, right? I wouldn't write stow alpha k. I would just write, show that I found k, say it's approximately 0.115, and then I was naming that k, and then I'm allowed to use the k here. Now look at B. B is asking me at what rate I have to use the differential equation here. But look at C. C is asking you at what time should oil, not a rate of oil, just gallons of oil. This I have to use the original, or Y, the one I just got in part A. So let's do part B first. At what rate is the amount of oil decreasing? So I expect a negative rate when there are 600,000 gallons of oil remaining. So remember, my derivative, the derivative of y with respect to t is ky, but my k is negative 0.115. Y. Well, remember, y is gallons and t is time in years. This is gallons of oil. So the rate of change in gallons per year, right, gallons per year, is negative 0.115 times gallon, right? So what am I going to put in for y? So you're going to put in, what did I ask for, 600,000? Times the rate of change would be negative, use your calculator for the, I wrote negative 0.115, or I could have just written k again because I defined k here. Now I will round an answer, and I got negative 69,314.718 units. Now let's answer C. C I guess I'm going to have to erase some stuff, right? I think I have room. C needs me to go to the original equation because it's asking me for gallons. Actually, it's asking me for time given gallons, right? So since they're asking me for a time given the gallons where I'm not profitable, well crap, what is that? Oh, right. I will no longer be profitable, so that means losing money, when there are fewer than 50,000 gallons. So what they're asking me to do in Part C is say that at what time, I want to know when there's going to be 50,000 gallons, right? What is that, 5 times 10 to the 4th, I guess? That's going to go in for Y, and I'm going to solve for T with the K I know. And remember, I've defined K, so I can leave it as KT. Divide both sides by 10 to the 6th. Five over 100 is usually 1/20th. ln both sides. Remember, K was negative, right? It was negative 0.115. Fortunately, because when I'm solving for a time, I sure hope it's a positive time, but remember, ln of a number between 0 and 1 is going to be negative. So ln of 1 over 20 is going to be negative. And then divided by my K, and I got 25.931. Can't read my writing for this. And what was my time in? Years. Alright. Note your homework. And then in your notes, we are going to explore not exponential growth, because that's unlimited. Remember, exponential growth, or decay, but just for time's sake here. Remember, as time goes on, if you're exponential, right, that says your population grows without bound as time increases. Well, that's not too realistic, right? And I don't care whether you're talking about population of people or animals or coffee shops or money. Whatever there's going to be some kind of bound on growth, even if you continue to grow, right? So this is the title of your notes. Logistic growth. Logistic growth is growth that is slowed by population limiting factors. So if I'm talking about animals, right? It's the resources. It's the how much food is there available? There's too many of them, and so now there's sickness because there's not enough food to feed all of them. The environment is constraining. If you're talking about coffee shops, right? Starbucks is a great example. This is a case study of. They exploded and they had exponential growth, and then they put more and more stores, and all of a sudden their profits started to still grow, but not grow as fast. So all kinds of really interesting applications to logistic growth. So here's a picture of a logistic growth curve for fur seals. If any of you have ever seen these live, they used to be in San Francisco. I think they've migrated up. We saw them in Oregon a couple summers ago. They're very loud. They yell at each other a lot. But here you can see these breeding male fur seals in thousands. As the years increased, their growth, right? Their growth did increase exponentially, right? Here's their population, right? It's growing exponentially. You can see the exponential curve right here. But then started to level off, right? And looks almost asymptotic here at 10,000, right? As time goes on. Now look at the rate of change of that logistic curve. Can you see that the rate of change over here is what? What are the tangent lines? Tangent line positive and higher, tangent line positive and higher, tangent line positive and higher, tangent line still positive, but the value of the slope is lower. Value of the slope still positive but lower, value of the slope positive but lower, value of the slope pretty darn close to zero. The rate of change of growth over time became zero or very close to zero. Now this is a mathematical model. In reality, most populations do something like this. They will increase over time exponentially, especially if there is a known limiting amount, population amount. If this is the maximum carrying capacity, right? Growth is very quick right here at the beginning, right? Unrestricted growth. Then, as you start to, food decreases, space decrease, or there's sometimes with the carrying capacity, real populations, might even shoot above this, and then some catastrophic disease drops it, much lower, and that it really is more chaotic around this carrying capacity. But for mathematical models, our logistical model does just fine, and it's pretty interesting the history of this. That and I'd have to look it up. I can't remember off the top of my head the years this occurred, or the mathematician that took. It was an English guy, economic guy wrote, or population study man, let's just say that, postulated that this whole idea of a carrying capacity and this catastrophic behavior around the carrying capacity was more realistic description of population growth than exponential, unlimited growth. And a mathematician, I believe he was German, read this English guy's paper a number of years down the road and was like, I bet there's a mathematical model to represent that, right, that is different from just your exponential model. And so, it's just, people just, you sit around and you think about stuff, right? It's pretty cool. So for our purposes, we are going to define, just as a letter, M to be that carrying capacity, and assuming that we know what the maximum population size that some given environment can support. Here's our previous exponential model. Right, and this, as we said, exponential growth occurs when the rate of growth is proportional to the original amount. That's what that says, right? The equation, this mathematical model, says that, right, exponential growth is proportional to the amount of the population. And that's where this comes from. The rate of the population growth, right, rate of change of growth with respect to time of the population is proportional to the amount of the population that exists. So the question becomes, well, what if we want to say, we want to kind of start from that, but then say we want to have an equation that represents the rate of change of the population relative to that carrying capacity, that M. So if we do start with proportional to the with the population that's present, can we multiply by some expression that would represent kind of quick growth, as long as you're not near the population, the maximum carrying capacity, and slower growth if you're nearing that carrying capacity. So I want you to think about if I had a 1 in here. If I had a 1, if you're multiplying the differential equation Kp for the exponential growth by 1, isn't that still exponential growth? True? And if I want exponential growth when I'm not close to the carrying capacity, I want something that is smaller than 1 but close to it, relative to that m. Remember, m is the carrying capacity, maximum. How about a ratio? Let's have a ratio of your population to the carrying capacity. So if I'm going to put m in the denominator to suggest, the entire carrying capacity. What could I put here if I'm at my carrying capacity, right? What if this was m over m? Wouldn't this be a 1? And what is 1 minus 1? That would make that 0, right? And what is 0 times Kp would be 0, which means your rate of change, your rate of growth would be 0 if your population was at the carrying capacity. But what if your population was below the carrying capacity? What if your population here was not quite at your carrying capacity? So if this number here represents the carrying capacity of the population, right, your environmental, and this is your population, if this population is, let's say m was 500, let's say m was 500. If your population is very far from 500, so let's say your population is only 2 or 10, right? If this number, if p is small, right, a small number over m, what's that going to be? Right? Isn't that fraction going to be close to 0? If p is small, then p over m is small, right? And then 1 minus p over m is close to 1, true? And if you're close to, close to 1. And if you're close to 1, 1 minus something, right, then this whole expression here is close to 1, and 1 times k times kp is kp, which is very exponential. Versus if p is large, approaching the carrying capacity, then p over m is close to 1. Not 1 minus p over m, just p over m itself is close to 1, which means 1 minus p over m is close to what? Is close to 0. So if this whole thing is close to 0, then your rate of change, right, your rate of change of growth is close to 0. Now that's a whole bunch of abstract explanation. You don't need to know it. You do need to know this formula, however. So this statement, the constant k, is called relative growth rate. And the only reason I give you this is because sometimes AP refers to K instead of the constant proportionality. It refers to it as relative growth rate. I just wanted to give you that vocabulary. But this equation, given the carrying capacity of M minus P over M, I want you to recognize that what I had, sorry if I go back, right, this equation, Kp times 1 minus P over M, I can rewrite that, right, with a common denominator, right? If I turn this into M over M, this is M minus P all over M. That's where this comes from. So what it means is the growth rate is proportional not just to P, right? If you're just proportional to P, that's dy dt or dp dt is equal to just proportional to the amount present. But for logistic growth, you are both proportional to the amount present and a fraction of the capacity that remains, right? A fraction of that carrying capacity. One minus P over M is how you'll see it in the book sometimes. So here's our logistic differential equation. Some books just take this denominator here, right, because technically this is over 1, of course, so just they put the M over here. So logistics differential equation, you do need to recognize. You need to recognize this. You also need to recognize it is still separable. How do I know it's separable? Because the derivative of a function or relation P is involved with P. P is your dependent variable and P is on the right side of a differential equation. That is separable. Please, 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 in May, you're not going to see it coming. You're going to be given a differential equation and your variables are going to be on opposite sides. You've got to remember to always, when you're dealing with derivatives, differential equations, you have to have the correct variables on the correct side before you anti-differentiate. So yes, this is a separable differential equation. And we can solve it. It's annoying to solve. The first thing I did was, right, since I recognized this was separable, I left the K, right, which is just a constant, proportionality, right? I left the K on the right side, and this M, which is also a constant. So this is just a number. Doesn't have any variables with it. And then I divided by P over P times M minus P. This is a partial fractions problem. So ignore the derivative stuff right now. Ignore this stuff and let's just do partial fraction work. The fraction on the left was already factored. And I just have to find A and B. Since I don't have any variables in the numerator, I can't use the heave-aside method really, right? But the numerator is just 1, so this is not really that bad algebra. And notice that I get 1 over M for both A and B. So now I'm going to go back and do calculus. And I'm going, since the A and B were the same over here, right, I replaced this fraction with these two, where A is 1 over m and B is 1 over m, and then I just factored the 1 out of 1 over m to the other side. The n's canceled out, and then really I was anti-differentiating, right? So the antiderivative of 1 over p is ln of p, and now we're doing with populations, right? So population, so I dropped my absolute value because we're dealing with populations assuming that we're doing growth greater than 0, and your maximum capacity is going to be higher than your population. Then I use my properties of logs to create a fraction, and then I'm going to e2 the both sides. So I dropped the ln so I could e2 the both sides. Then I reciprocated, right? I reciprocated both sides, so I flipped this. I flipped this, but when you have 1 over e to the positive stuff, can't you make that e to the negative if you want? So that's what I did there. Separated this, so I have m over p minus p over p, which is where I got this 1. Added the 1 to both sides, then reciprocated, right? So this is m over p, this is over 1. So p over m was equal to 1 over all of that stuff, and then of course I multiply through by m. Then I separated out the constants. Don't ask me why, but for these differential equation problems, logistic ones, they like to call the constant a. You can call it y sub 0, p sub 0, whatever you like. This is the solution to the logistic differential equation of the form the derivative of a population growth over time was k constant proportionality times the initial population times a fraction of the carrying capacity. And remember, there's a couple different ways to write that. Some books float the division by the carrying capacity here, and then just have m minus p in here. Sometimes it's kp times 1 minus p over m. The point is, all that solution solving the separable differential equation, logistic separable differential equation, you don't want to do that math. You want to recognize, if you recognize, just like with differential equations, AP will allow you to skip all of that nasty calculus if you recognize logistic. You can skip all of that calculus as long as you've memorized what the solution looks like. If you recognize logistic growth, separable diff EQ, you're asked for the solution, you can skip all of that calculus, partial fractions, blah, 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 and skip right to here. So let's try an example like that. Oh, before I do, I just want to highlight the logistics separable differential equation. You can, if you recognize it, you can go right to the logistics model that, of course, yes, you do have to memorize. Just to confuse you even more, your textbook likes a different version of this. Your textbook, their K is the constant proportionality already divided by the maximum carrying capacity, which means their logistic equation, though, to counterbalance that, they have an extra m down in the denominator of the logistic growth model. It doesn't matter, I promise you, there you get the same results. It doesn't matter which one you use when you're asked to write a differential equation. And I do think that AP, in my experience, if you're asked to recognize a separable logistics differential equation, it's in this form. Not all the time, but that's why I teach the one in the yellow box first. Alright, so let's look at this. So you have a handout, and I have a logistic growth model of some bears. Population of bears, like in Yosemite or whatever. There's, they know how many bears they have, they know how many bears they start with, and they know the carrying capacity of the environment. So let's suppose that it was 10. 10 grizzly bears were introduced to this national park 10 years ago. There were 23 bears at the park at the present time, but the park can only support 100 bears. Assuming a logistic growth model, when will the bear population reach the following numbers? Now this right here, that's my carrying capacity, right? So it's not going to go over 100. I'm asked to round my answers as well to the nearest year. So if you're assuming a logistic growth model, you can again do either one of the ones on the previous slide. You can either have the one with the M here or not. I choose to want the one without the M. This is the model, and just like I did on the warm-up, the first thing I do is I start with this model and I use my initial condition and my carrying capacity and my second point. Right, 10 years later, there are 23 bears. And this is just algebra. This is no calculus yet, right? So put 10 and 0. Nice example because A is 9. Right? So step 1 was no calculus, just the solution to logistics differential equation. Okay. Had to get my carrying capacity, had to get 2 points. I need 2 points because I'm going to be solving for 2 unknowns. My A, which is not really my initial condition, I shouldn't have said that before, it's kind of a manipulation of your initial condition, right? And then this constant proportionality. I need to solve for both of those, so I need 2 points. So I just solved for A. Now, step 2. Solve for K. I should have said, write down the solution to the separate differential equation. Use M and 2 points, one of them being the initial one. No, Laura. Initial condition to solve for A. 2, solve for K using the second point. A lot of this is calculator work, right? Store in your calculator. Instead of using K, I'm just going to round this. You know, to write it down, I don't have to follow the 3 decimal places, right? Because it's not, that's my final answers have to be to 3 decimal places, although in this problem they asked me to report my answers in years. So it's okay for me to write this negative 0.1 here, right? As long as because this is not my final answer, as long as I stored all of those values really in K. So I now have my population model, right? This is not a differential equation, this is a population model, right? Bears in terms of T. So if you get your calculator out and enter this equation into your calculator, think about your window, right? If your maximum carrying capacity is 100, you might want to make your Y max maybe 150 or something. You don't need any negatives for X max or Y max, X min or Y min. And they gave us a point of 23 years for time, so I don't know, maybe make your years go to 50 or something. Oh, I made it go to 100. And you should see a very nice logistic curve. And then they asked me to find things like, what about, you know, in the original problem, I can graph in Y2. They asked me about 50 bears. When will there be 50 bears in the park? And it's rounding to the nearest year. It's at about 22 years. Then it asked me for 75. So in Y2, I graphed the line Y equals 75, found the point of intersection. That was 21 point blah 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 something. But the 100 is really a silly question, right? Because I can't really use intersect. This is really a limit question, right? At 100 years, since 100 is the carrying capacity, I mean, I can use my calculator and just kind of trace, you know, I can actually just trace and see about when do I think is the first time it hits 100. But this is really asking me for the end behavior of this function. Is, you know, when, and for me, just to approximate, right? Approximate when do I think was the first time I got the closest to 100. This question they're not going to ask you, right, in this way. They're not going to ask you for an exact, but or even to, unless they're asking, they give you a graph and ask you to read, right? But it's at approximately 75 years. The important thing for you to recognize was this was M, right? That is the bound. That is the end behavior. Now, that was all. That's the equation for the population itself. What about the rate of the logistic growth? Well, since it's a logistic model, I already know the differential equation that goes with it. My K, right, this is my K, It was actually 0.09 something 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 over m, right? K 0.09 blah 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 100 100. That's where that comes from. So here's a question that might be asked given this differential equation, which, to be honest, for the calculus exam, they're going to ask you more things about the derivative than they are about the original. So here's the derivative, and they're asking you, when does the rate of population growth start to decrease? Right? So think about that. When does the rate of population growth, not the population growth, the rate of the growth. Well, again, I kind of showed you that before, right, with tangent lines, right? Tangent line, rate of change is positive, but steeper, positive, steeper, positive, steeper, positive, steeper, still positive, but oh. Matter of fact, this is when I change from concave up to what? Hey, there's a word I use for that, isn't there? Poi. And in calculus, how do you find poi? When the second derivative, since this is a differentiable function, I don't have to worry about when the derivative doesn't exist. When the second derivative is equal to 0 and changes from positive to negative, concave up to concave down, that's what I'm looking for. Do you have a second derivative? I don't think so. What do you have? You have the first derivative. How can you take a first derivative and find a second derivative? Gee. Now I have to tell you to be careful. Careful, careful, careful. This is a derivative of y with y's on the right side. Think about that. What does that mean? Implicit differentiation, kids. That's right. Implicit differentiation. Right? Remember what happened when I asked you to differentiate? What if I said, I want you to take the derivative with respect to x of, what do we have? Like x squared plus 2xy minus y squared is equal to 7, right? Take the derivative, implicit differentiation, because you were taking the derivative with respect to x, and there were the derivative of y with respect to x, but there was y stuff here. So you have to remember that when you're taking the derivative, firstly notice that I distributed, right? I just distributed so that this looked nicer. It's just a quadratic, right? So the second derivative, what is the derivative of 0.01 times p, right? And 0.001 p squared. So really what's happening here is this is 0.1 dp dt minus 2 times 0.001 p to the first times dp dt. And I just factored dp dt out. That's all. But hey there, I already have an expression for dp dt, don't I? Because remember, I'm trying to set this equal to 0. dp dt is right there. So when is the second derivative equal to 0? It's when that's equal to 0 or that's equal to 0. right? Because it's a product of two things, one versus the other. Now remember, we are talking about rates of change when the population and time is all greater than 0, right? So since this is always positive, right, because the first derivative, the slopes are all positive. Right, on here, slopes are all positive until way over here where they're still just close to 0, but they're still positive, right? Then all I need to know is when this factor, since this factor, dp dt, is always positive, when is 0.1 minus 0.002 equal to 0? Right, subtract 0.1, divide by negative 0.002, and you get 50. Don't stop there. Right, I bet you were wondering what that red box was for. The question was, when does the rate of the population growth start to decrease? Is this a when question? Is P a when question? No. Sadness. I have an equation that gives me when, doesn't it? I have an equation that gives me a time when I know a population. So I know the population will be 50 when the rate of population starts to decrease. So I'm going to take that 50 and I'm going to plug it in there. And I can do a bunch of algebra, or since I have my calculator, I can just plug in, hey, I think I've done this already. Didn't I do this already? Ah, that's called planning, right? I already, on the previous slide, had you put 50 in, right? You graphed it, you found the point of intersection, and it was 21.9-ish, right? So we got 22 years. But this, right, when, make sure you're answering the question. Now let me show you something else too that you can, another way to think about this without having gone through that algebra. And this will be a shortcut to try to avoid that math I just did. I want you to look at the first derivative over here. The first derivative, and use your Algebra 1 brain. Isn't that a parabola? That's a parabola, right? That opens which way? Down. Now, you can't forget that these are p's here, right? So I'm going to come down here. I'm going to draw little axes. I'm not going to draw my time versus population. I'm going to draw my population versus the rate of growth of the population with respect to time. Now, talk to me about when the rate of growth is 0. Right? The rate, would you agree that if you don't have any, right, before 0, you're like, right, your original? Right, so let's say even right before they put the initial bears in there, right? Aren't you at, your population is 0, is your rate of change 0, right? Your growth rate would be 0. When else is the rate of population growth 0? Right? Over here. So wouldn't that be, right, your maximum? And what was our maximum? It was 100, wasn't it? And your population grows and then decreases, right? Now this isn't, remember, this is not the population, this is the population growth, right? The rate of change of population. It's a parabola. But this parabola is a first derivative. When is the second derivative equal to 0 if you're looking at the graph of the first derivative? where the first derivative has a horizontal tangent, changes from increasing to decreasing, right? Where the first derivative changes from increasing to decreasing, your second derivative is equal to 0 and changes from positive to negative. But since this is a parabola, this is the vertex of a parabola, and what is one of the beautiful features about a parabola? And if this is at 0, a maximum population of 100, where is this? Wow. And let's be clear, 50 is exactly half of what now? Your maximum carrying capacity. Aha! If your mind isn't jello by now, use your slope field program by typing in the derivative into y1, the actual population equation into y2, and I would arrow over, use on your calculator, arrow over and make, the choice. You know how you can arrow over and put your cursor near the equal sign and then hit enter and make this a thick line? And then in y3, also with a thick line, type 50. Now you already had this, you probably already had this equation in y1, right? So just move it down to y2 and 50 down to y3 and just enter this so you can see the slope field. And again, you'll see the point of intersection, right? You can see that you'll be able to see the point of intersection right there at poi. And when you look at the slope field and our solution running through it with our initial condition, hopefully you can see the shape of the slope field. And that's why I actually like to make my y max a little bit higher than 100. And you can see how our solutions, really nicely graphs right through that slope field. But the nice thing to know about, if you're going to look at it graphically as well, right, that this 50 is exactly halfway between a 0 and m. That will always hold for logistic separable differential equations. This equation, the second derivative will always be 0, or the maximum on this first derivative, the maximum of this first derivative will always be at half the carrying capacity. So as long as you have this separable differential equation, the point of inflection, y coordinate, will always be m over 2. So poi will always be t comma m over 2. And oftentimes, at least we've seen in the past couple of years, AP does ask this question, but they ask for the when. When is the carrying capacity at its greatest? When does the rate of growth start to slow? Da 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 da. Various different ways of asking that. You don't really have to do any math if you remember that the y coordinate of poi is always the carrying capacity over 2 as long as you have this logistic growth model. Alright, have fun with that homework, and I'll see you tomorrow. Thank you.